Good morning to everybody. Now we are going into the next part of our lecture on the performance criteria and controller tuning. This in the book is covered partly in chapter 16 and on the end part of chapter 16 and also on chapter 18 where we have the major part of this part, controller tuning and performance criteria is talked about in chapter 18 of the book. It comes together. This both performance criteria and controlling sometimes it's a topic related to one another. In trying to get performance criteria, we can also tune the controller. When you use different control tuning, we want to check what's the best, we use the performance. So they are interrelated to one another. So that's why we are using this part. This topic is together we introduce this topic criteria as well as the controller tuning. Okay, this is a typical control system that we can use to demonstrate this issue. It doesn't matter really too much about the system. It's a second order system with a date time system, but it can be any other system. But mainly it is the controller that we are going to see, the controller that we are going to what you call highlight further. This is the controllers that we're going to try different controllers and use it for our performance criteria. At the end of the day, we want to see how the performance of C with respect to changes in U and changes in R. Okay, changes in R. Okay. Okay, for simple qualitative criteria for different controllers, we can see that this is going to be sort of response that we will get if we have a P controller. We'll get sort of response with an offset here. Okay, same thing with the PD controller. We'll get less overshoot but with an offset. If we use a PI controller, we will get more oscillation, but at the end of the day, it will be no offset. We'll use a PID controller, less overshoot, slight oscillation and no offset. So basically, we have a choice basically what sort of controller we want to decide for our system. Of course, we may want to have a PID controller, which looks like the best, but at the same time, we have a disadvantage. We have more tuning to do in PID. PI, we got less tuning. So PI is good also, you get less offset, but there's more oscillation there. P is got offset, but the tuning is more easier. P and PD easier. You don't have to tune too many controllers. And some offset may be desirable. So there is some decision to be made. It's not every time we're going to just use PID. PID also may not be suitable for some system. PI may not be suitable maybe for some system, P and so on. So these are the criteria or the choice that we have to make. We have to decide on first what are the controllers we're going to use, and then how we're going to decide which one gives the best response for us. Okay, there's no one best response. We have to use different criteria at one time to decide which criteria is the best at the end of the day. It doesn't. If for one criteria is less, for one criteria is better, for one criteria is less better, and one criteria is better. So this is why we have this study to check what are the criteria that we may use to decide which is the best controller we want to use, and also at the same time, for some cases, what is the best tuning parameter that we're going to use. Okay, so the decision of the controllers we're going to use can be based first on the type of controller we want to use. First, qualitatively, we can also decide, or quantitatively by calculations and all that we can also decide. And quantitatively is normally related to the performance criteria that we're going to use. We can decide which is the best controller for us based on based on calculation performance criteria, which is quantitative method. Qualitative based on experience, on our knowledge of how the controllers work. And then after that only we will also we'll have to talk on the controller tuning. As I said, sometimes the controller tuning can be related to performance criteria. If you use ISE, it will also solve for the controller tuning as well. But there are also fixed methods of control tuning. There are also methods related to the performance criteria to get the control tuning, which we just mentioned later. So the first, of course, obvious thing to do is to decide the controller you want to use based on qualitative understanding of the behavior of the controller. For example, we want to see what system are we going to use first of all. Okay, so if we have a certain some system, for example a level system, it is possible just to use a P controller, because although P controller have an offset, but for levels a slight offset is not a major issue. Something that we don't want for flow, temperature, all quite sensitive to offset. Important not to have offset, but for level it may not be so critical. So a P controller will be sufficient most of the time for level system. With slight offset doesn't matter too much. 0.1 meter, 0.01 meter, maybe slight offset there may not affect the system so much most of the time. So we can still use a P controller for level systems, but not for other systems maybe. Okay, for systems with flow system, we cannot use the PID controller because of the disturbance. So we have to use a PI controller. P controller may not be sufficient. For flow, we need exact flow, actual flow. So PI controller maybe is good enough for flow controller. So we do not have to go into the quantitative. We can already decide for the flow system is a PI controller. For other systems, for slow system, temperature, concentration, the PID would be normally the better one, the more suitable, because the PID would be counter effect the slowness, the delay in how the system responds. So normally we would like to use a PID controller. So these are some of the qualitative methods we can use for some system without having to go into detail on calculating, checking which is the best controller, which will give us the best what you call performance criteria and so on. We don't need some system we don't need. Based on qualitative, we can decide what the controller we want and go ahead with that. For the quantitative system, then we can use this to decide the quantitative based on quantitative reasoning. Then we can apply a few performance criteria for our system, as you can see in the next slide. Basically, the performance criteria are broken down into two. One is the steady state criteria, which is at one point only, and one of them is the offset, which is at the end, the time infinity at a very long time. And the other is the dynamic criteria. Dynamic criteria is broken into two types of criteria. One is at certain times, dynamic by certain time. The rise time. What is the rise time at that point? What is the decay ratio for 2 points? What is the overshoot at the first overshoot point, and so on. So these are dynamic criteria, but they are at certain time. But if you want a dynamic criteria that covers from beginning until the end, then we have to use this more rigorous method, the ISE integral square error method, the IAE integral absolute error method, the ITE integral time absolute error method. So these are more detailed, more comprehensive, covers from the beginning until the end. But again, as I said before, in the real world, the real thing, we may have to use all these criteria together. It may satisfy some criteria, give good result in certain criteria, but not so good in certain criteria. It may be good in certain, it may not give an offset, but it may be very high rise time and so on. So those are the things we have to look, we have to balance. There's no one method that will give the best for all. Okay, sometimes this one will give good, sometimes this one gives not so good. You have to make your own decision on how you want the response to be. For example, if you look at the different responses here. Yeah, you can see the what you call P will have the offsets. Okay, P have offset. You get offset, PD offset, but it's not too much oscillation. PI you have more oscillation, no offset. PID slight less oscillation, with less oscillation, with no offset. So you have to decide, maybe for certain cases, I said just maybe you can have P. You can afford to have small offset, and it doesn't give too much oscillation. You can accept with P. But if you don't want offset at all, you have to choose PI or PID without offset. But again, you have to decide on what criteria. You have no offset for both of them, but how this response goes before you get the no offset. Yeah, you get a lot of oscillation before you get no offset, so you get less oscillation before you get no offset. Sometimes we may have a lower overshoot but more oscillation. Sometimes you have a high overshoot but less oscillation. So you have to decide all the different criteria using dynamic and even the steady state. Offset is the steady state, that's one issue. But offset alone will not tell you which is the best if you have no offset, but how does the response goes before you get the offset. So that will have to use the dynamic criteria on overshoot, the rise time, how fast it goes up, the decay, how fast it decay, and then you have to use the whole spectrum of error, ISE, IE, and so on. So that's why we need to have all the different criteria sometimes to come together to make a decision. One criteria may be good, but for the other criteria it may not be good. So these are different criteria you have to use at one time to decide what is the best performance that you want. So that's why we have these performance criteria to make a decision on what is the best controller for your system. So for the dynamic criteria throughout the whole spectrum, we have the ISE, the Gauss square error, where you get from 0 to infinity, calculate the errors from 0 to infinity, square it. Of course, you have to square it. You cannot use the actual error. You can think for yourself why that is the case. You cannot just use the error. Then you have the integral absolute error. Again, you have to use the absolute error, the squared absolute error. You cannot use just the error from 0 to infinity. Infinity in this case means the final response time, which may be plus or minus the final value, depending on what response time definition we have done before. It's not up to totally. It's up to how long you're going to calculate your values. You can also have the time weighted, where you have a response, but the response oscillation going quite long. So you have to use the time to decide whether that's good or not. So E is the error set point minus control variable. And for system there's no offset, of course E equals to 0. If you do not have an totally fully damped system, there's no overshoot, no offset, the whole error is 0. But definitely most of the time the error is going to have some error, but what you're going to do is to minimize the error. May not be getting zero errors. Zero errors, as I said, is more for critically damped system. But you'll have some errors, but you want to minimize to the best of your ability. So this is how the error is defined by this. Error is defined by the value divided by the offset. That is the error. The offset, the value divided by the set point. Yeah, the value divided by the set point. Yeah, this is the error. E. Okay, and basically by calculating the squared error, the E squared error, basically you are calculating the area under the curve. So you have basically you are calculating the area under the curve, under this curve, the whole thing under this curve. Okay, not complete, but it's the whole thing yellow. That is basically the error for this PID one. That is the error you are calculating. So you are trying to minimize this. By minimizing this, means you are minimizing the overshoot and the oscillation to get to the minimum and quickly get to the final value with offset equals to 0. So that's what you're doing using this dynamic criteria covering the whole spectrum. And so in certain cases, you have to calculate the dynamic criteria for all the different types of controller and decide. And and use these criteria to make a decision on what is the best PI controller. And also maybe different tunings, different controller tunings will be used, calculate the IE, ITE, and then get the smallest value for your system to make the decision for what is the best controller. So these are the way you are going to normally design your controller. Other than just using the straight forward controller tuning, you can also use this to decide, try different tunings and calculate the dynamic activity and decide what is the best controller for you. Of course, you can do it easily in Simulink and on computers to make all this decision and using all the different criteria, not just one, IE, IT, AC, the offset criteria, the overshoot, the rise time. You can use all the criteria and make a decision. I said it will not, you will not get the best for all. Some criteria may be good, some may not so good, but you have to take you have to what you can take the best for most of it. They satisfy most of the criteria. You have to have a plus and minus issue here. It's not just one method will give you the best result. One control will give you, not necessary. So that will, by looking to all the different results, you can make a decision on what type of controller, what tuning you can use for this system and so on. So these are why we are using this criteria. Mostly these criteria are calculated using computer program Simulink. You see the example in the next class on how we use the Simulink to calculate all these criteria and make a decision on the type of controllers and the tuning as well for the system. So, and for that, our next part we will cover the controller tuning method that will be used for controller tuning, not basically using the dynamic criteria method, but the standard methods that we use for controller tuning, and that we will cover in our next class. When you do your project also, you'll be using all these criteria, the different tuning method, all these criteria to decide finally what is the best controller for your system for the set point and disturbance change. So it has to be for both set point and disturbance change. That will give you the best criteria, servo and the regulatory control. And in this case, you'll see IC will penalize the response that has large errors, which usually occur at the beginning of a response because the error is squared. So when you have a large errors, square it, then it becomes big, and that's why you try to more optimize to get the smallest possible error to the best controller choice and controller tuning. And it can be only used for big error. Anything less than 1, you cannot use IAC because when you square a small value, it will become smaller, and that does not give the reflection of the real system. It looks small, but actually it's not small because you squared it. So you have to be careful using IAC. What sort of criteria you have to use. So, but for those other ways, with small error, big errors, you can use IE. Will be less severe in penalizing a response for large and treat all errors in a uniform manner. So, other cases where you do not have too small errors, you can use the IE method. And for errors that persist for a long time, you can use the ITA method. But using the computer program, you can calculate all 3 methods at one go, and then decide what is the best, smallest error that you will get to decide your controller and tuning, and use this also as a way to what you call tune your controllers, to tune and also to get your criteria fulfilled. So you can do it easily in Simulink and all the controller methods for your project, and this will be given. The example will be given in your other class where we have the Simulink example to show how these things are calculated. Okay. So we will finish at this point and we'll do the control tuning in the next part of the talk. Thank you very much. Assalamu alaikum.